Hello everyone. Most of us have seen or heard decibel being used to indicate the intensity of a sound level or the power of an electric signal. So what does decibel represent exactly? What does it mean? Well, decibel is a unit of measurement, but it's not a unit of measurement in the same sense of other common units of measurements such as kilograms or meters. Okay, so what does it mean when you see dB near a number? Well, it's just an indication that this number has been calculated using a logarithmic function or measured using a logarithmic scale. Okay, so basically the logarithmic function converts the absolute measurement value to a dB value. And the question is, why not sticking with the absolute measurement value? Why do we have to use the logarithmic function? Well, that's what I will explain in the next slide. Let's take the example of sound signal and let's see how decibel is being used. Okay, so let's talk about the dynamic range of sound pressure. Sound pressure is what's being used to measure the volume or the loudness of a sound signal. So the minimum value that a human can hear is called the threshold of hearing, and it is around 20 micropascal. The maximum value of sound pressure that a human can hear is around 63,200,000 micropascal. So as you see here, you have a huge range. This span or this range makes working with sound pressure values impractical in normal use. So this is the reason for using the logarithm function. It will make it simple to describe the wide dynamic range of sound signal. How it's gonna do that? Well, by simply compressing the sound pressure signal. So the dynamic range will be reduced by applying the logarithmic function. Okay, so how do we calculate sound pressure in dB? And actually, when it's in dB, it's called sound pressure level. When it's in Pascal, it's the absolute sound pressure, or sometimes they just call it sound pressure. Okay, so we use this mathematical function, which is the 20 logarithm, the measured pressure, which is the absolute sound pressure, divided by the reference pressure. And here, the reference pressure has been chosen to be the threshold of hearing. Okay, that is the 20 micropascal. So when you apply this equation or this formula to the dynamic range I showed you before, you get this compressed dynamic range that is from 0 dB to 130 dB. And as you see, it's much better to work with these numbers here, 0 to 130 dB, than working with the millions that I showed you in previous dynamic range, where the maximum was 63,200,000 micropascal. Okay, so let's talk about a relationship between the absolute sound pressure level, which is in Pascal, with the sound pressure level in dB, the corresponding sound pressure level in dB. So basically, as we saw before, your threshold of hearing is 0 dB, okay? And that is the lowest you can hear. If you multiply that sound by 10 times, well, your dB gets increased by 20 dB. So your measured signal in dB is 20. If the threshold of hearing is multiplied by 100 times, the measured sound pressure in dB is 40 dB. And I also want you to understand that if you have two loudspeakers, one of them is 20 dB and the other one is 40 dB. It doesn't mean that the one with 40 dB is twice louder than the one with 20 dB. That's not the case. As you see from this table, the loudspeaker with 40 dB is 10 times louder than the one with 20 dB. Okay? And one more thing to say is that doubling sound pressure will increase the sound pressure level with 6 dB. To get you a feel of how these decibel values sound, I have here a table that associates some common sound to their corresponding sound pressure level in dB. Now, if you want, you can pause this video and spend more time with this table, or you can download a sound meter app, and there are many of them, to your cell phone and experiment measuring different sounds. Thank you very much for watching. If you like this video, please subscribe and share, and hope to see you in my next video.